Hi, my name's Dustin Koha, and I'm going to be solving a fluid mechanics problem for you today. This is problem 6.78 from our textbook. And so basically the problem is you have two plates and one of the plates is moving at velocity u, and the other plate is fixed in space. And between the plates you have a fluid, so you have some fluid in here that's going to move in some way. And you're going to have some velocity. So basically the goal of this problem is firstly to find the velocity distribution. So basically, what does this shape look like? How does the fluid flow? So I'll define our coordinates as well right now. So we have our x, we have y, and we have z into the page. So velocity distribution is how does this fluid flow in our x direction. And secondly, we're going to find the flow rate between the plates. So our flow rate between these plates. So firstly we want to define our assumptions. So with these assumptions, firstly we can assume that our velocity in the y direction is equal to 0, and also that our velocity in the z direction is equal to 0, which basically means we only have velocity in our x direction, which is that way. Also, we can say that anything with respect to x will be 0, and anything with respect to z will be 0. This is basically, so in the x direction, it's constant. Nothing's going to change. Whatever this field ends up being, or this distribution, it will be the same anywhere in your x coordinates. And same as the z. Also, this is there's no time dependence, so we will say that this is true as well. So to start this problem, we are going to look at the Navier-Stokes equations, which are just these equations. So we're going to be looking at the Cartesian coordinates, because this is not a polar coordinates problem. So we'll first start looking at the x direction. So we have, this is our, just write this down quick. Okay, so this is our Navier-Stokes equation for Cartesian coordinates in the x direction. So to solve for the velocity distribution, we basically want to get rid of as many terms in this equation as we can using these assumptions. So we'll start and we'll go through the equation. We can see that this term will go to 0 because you have with respect to t. This one's going to go to 0 because you have x. This one will go to 0 because v is equal to 0. This one because w Oh, also in the problem statement we have that the pressure distribution along the x is 0. So basically that means it's not pressure driven. So we can say this is 0. We're neglecting gravity, so that's 0. So now we just have these three terms. This one's with respect to x, so it's 0. This one is with respect to z, so that's 0. So now we can simplify this equation to that. And now all we have to do is solve for u, and we have the velocity distribution. So to do that we have to integrate twice. So our integration so our first integration we're going to get u simply is equal to c1. We'll call this our first constant because the integral of u is equal to 0, or integral of 0 is equal to c1. And then our second integral, we will get that u equals to c1y plus c2. So now we have this equation for our velocity in our x direction. And so now all we have to do is solve for c1 and c2, and we know the distribution. And to do that, we need to define our boundary conditions. So our boundary conditions are going to be the conditions we know, which are the velocity at this plate and the velocity at this plate. So the velocity when y equals to 0, we're calling this 0, and then y goes up. So when y equals 0, 0 equals 0. Because this plate is fixed, and we have a no-slip condition. So that means that velocity here is 0, and velocity here is going to be the same as the velocity of this plate. So that's our first boundary condition, equals u, and that's our second boundary condition. So now we can plug these into the velocity in the x direction and solve for c1 and c2. So with our first one we have 0 equals c1, c2, that goes away, c2 equals 0, and that'll get plugged into there, and now u equals c1 times b plus 0, so c1 equals u over b, and that'll get plugged into there. So now we know that u equals u over b, y. And this is our velocity in the x direction. So this tells us that the velocity between the plates, or the velocity distribution, is actually linear. So as we go up y, our velocity here will just be that distance y times our velocity b, or velocity u, divided by b, which is our distance. Okay, so that's A. So for B is pretty simple. So we know that flow rate is equal to velocity times area. So for this problem, it's kind of tricky, but basically what you do is just you can integrate from 0 to b. So we have our integral of our velocity, and then we have our dy, and we have our w. So that dy and w is going to be the area of that cross-sectional area where the water is actually flowing. Then we're integrating from 0 to b to account for this distribution. So this is just going to turn into u over b, and then we're integrating y. So what I did was I just plugged in u and then took out the u over b and then integrated y, so we get 1/2 y squared, and then that's from 0 to b. So now q equals w u over b times, this is b squared minus 0 squared, and this just turns into w u b, oh, forgot the 1/2, over 2 equals q. And that is our flow rate through the two parallel plates. And that's about it. I hope this helped, and yeah, have a great day.